All right, good morning, everyone. Hope we had a good weekend. Hope we had a productive weekend, some studying, some homework, reminders of your due dates. Well, really only one due date coming up, 1.5, the 23rd. That's a couple days from today. We're going to be doing 1.6 today. We will not finish this section today. This is a very long section. I will definitely be finishing it on Wednesday's class, so then it'll be due a week after that. Then the next section will probably take a day, and then you'll notice something a little weird, and I wanted to point this out this morning, that we go sections 1, we covered 1.1 even though there's no homework on it, so 1.1 through 1.7, and then there's this weird 3.6 part 1, 3.6 part 2 thing going on. So in an old edition of the textbook, 1.8 then is now 3.6, but in terms of where it should be placed for a pre-calc course, we still feel that it belongs in chapter 1's area. So we're going to cover section 3.6 as a part of an ending chapter 1, and it will be the last section for test 1. So the first test will cover sections 1.2 through 1.7 and then 3.6. Now, I don't know why the person who created this homework, because we all use it the same across the departments and several campuses as well. I don't know why they split this one into 2 parts. It's very unusual. It's the only time that's done through the entire semester. It makes no sense, but it is what it is. So just kind of ignore the fact that it's in 2 parts. It's just one part is half of the section, one topic, and the other part is another section. But again, this is really like 1.8. We are essentially calling this 1.8. So those will be the 7 sections for the first test. If I had to, put a ballpark on it, I would say we're probably going to be finishing this material Wednesday, September 30th. That's my best guess. Remember, that's just a guess. It's not definitive. We might be a little ahead, a little behind, especially with this format. Some days I find myself losing about 10 minutes just because of technology and not being able to see with this pen and blah, 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 rant, blah, blah, blah. So if we finish the test on the 30th, that means that the test itself would be the week after that. Something like the 6th through the 8th. I don't want to say that definitively yet, so it's still a ways away, but just know that that test is like 2.5 weeks away. It's coming up. Okay, so 1.6. Last time, and we spent like a day and a half, maybe 2 full days covering 1.5, which was solving quadratic equations. So again, as a reminder, quadratic equations, we learned 3 methods to solve them. Factoring, which we said in the real world only works like 2% of the time. Then we learned completing the square, which we said works 100% of the time. Every single quadratic in the whole world you can solve by completing the square. A lot of people don't necessarily like that method because of the weird mythology of it. Words are hard. The method. Just kind of the why are we having and squaring it, and I explained the reasoning, but it still might feel arbitrary to you if you didn't understand it and you don't practice it. Then we went over the quadratic formula, which we said is derived from completing the square, and we said that also works 100% of the time. And we said that on a test, if you don't follow instructions, as long as all it says is give the solutions, it doesn't ask you for steps along the way, which is atypical of me to do. And as long as it's right, it's right. If it's wrong, then you won't get partial credit if you use the wrong method. If you use the right method, you can say, hey, look at my work, and I might be able to give you a couple points. Someone just asked about quizzes. So as I said, quizzes are only going to be if I think they're necessary at the end. So no quizzes so far. If I have to change that, which I do not expect for this class, it's very rare. I do quizzes in the 161 class. So yeah, you don't have to do those. All right, so that was quadratics, factoring, completing the square, and the formula, the quadratic formula. And we said you have to have that formula memorized all semester. 1.6, other types of equations. Well, we're going to be doing other types of equations. Specifically, I'll go ahead and show you the long list we'll have. Polynomials, which when we say polynomials, a quadratic is technically a polynomial, but we're just kind of referring to higher order polynomials. Cubics, so something with an x to the 3rd, or quartic, something with an x to the 4th, quintic, something with an x to the 5th, and no one actually calls them those names. in reality, except for math nerds like me. So just things that have bigger exponents, polynomials. And you can see the 3-word instructions solved by factoring. There are many other methods outside of this course that we will not cover. That's the only type of method we'll have for that one. So the other types that we'll see before getting into those are radical equations, which means there's a square root in there somewhere. We'll have rational exponential equations, which means you'll have like an x to a number, but instead of it just being an x to the third, it's like an x to the 3/2. Then we'll have absolute value equations, which means, well, if there's an absolute value in there somewhere. And then we'll have equations that are in quadratic form. So those are the different varieties that we're talking about. Are they all varieties in the world? No. Will we get to some other varieties in this semester later? Yes. Will we cover everything possible? Not even close. That would take us 10 years and we still wouldn't finish everything. All right. So polynomials, nothing real crazy for the instructions, solved by factoring. So if you see an x to the 4th in an equation, you're going to try and solve it by factoring. If you see an x to the 5th, you're generally going to try and solve it by factoring. At least for now, because that quadratic form thing I mentioned will open up a different variety of polynomial as well. And we're not going to do a whole bunch of these. So example 1, because again, factoring is supposed to be inherent to us. And this is just an example 1. So we're going to solve x to the 3rd plus x squared is equal to 4x plus 4. We're going to find all solutions to x cubed plus x squared plus 4x plus 4. I think I might have said a plus here instead of an equals, but it's written correctly. So how do we solve by factoring? Well, you've got to go back to the instructions from a few classes ago if you're really, really rusty, but this is something that, again, should be pretty inherent to us soon. So when you want to factor, everything needs to be on one side. So you need to either move the terms on the left to the right or the terms on the right to the left. It's up to you, but there's a preference, in my opinion. It makes it easier. We always want the leading term positive. We always want this term positive to make the factoring as easy as possible. So we're going to, and I got to squeeze this in, subtract 4x on both sides and subtract 4 on both sides. If you wanted to rewrite this and just give yourself extra space in this vicinity, you could. But then that's going to give us x to the 3rd plus x squared minus 4x minus 4 equals 0. Remember, this is what we need for factoring. We need 0 to be on one side, everything else on the other. We gave you several different methods for factoring. You can go back to those notes. I've given you those, a lot of those notes from the very beginning of the semester, in fact, in the prereq stuff. And we said if you have 1, 2, 3, 4 terms, the only method that we have given you in here is factor by grouping, FBG. That's where you're doing a GCF for the first pair, a GCF for the second pair, and then you should hopefully have matching parentheses, in which case that makes a third GCF. So I'll show blue taking out the GCFs between x cubed and x squared. X squared is the GCF. When you take that out, you're dividing. X cubed divided by x squared is x, and plus x squared divided by x squared is not blank, it's not 0, it's 1. I gave us a super special hint that the middle number sign, the third term sign, this is 99.9 probably % of the time what the next sign is. This is the sign of the GCF you should be factoring out between 4x and 4. 4 is the only thing that goes into both of those. Excuse me. Open up our parentheses and divide it. Watch your signs. This is where people rush and make simple mistakes. I'm not going to say I've never done it because I have, but I very rarely do it. Negative 4x divided by negative 4 is positive x. And then negative 4 divided by negative 4 is positive 1. Then we have our equals and our 0. Now this x plus 1 is a factor of the first term and a factor of the second term. To be a factor means a product. So that means it's a third GCF. So here we have a GCF of parentheses x plus 1. So we write that GCF first. That's the rules for GCFs. We then open a parentheses. And I gave you a super special tip for what goes in there. It's you cover up the GCFs the parentheses. Now, if there were exponents with them, you'd only be covering up one of them. So there's, but that's not an issue for us yet. That'll be a calculus issue. And then what do you see left over? The x squared minus the 4. So that's what goes in the other parentheses. X squared minus 4. I know I kind of have the inks backwards, but I'd been doing the GCS blues and the remaining parts in black. So the x plus 1 was the GCF. It goes first. Then you had x squared from the first term, a minus 4 from the second term. You set that equal to 0. Now, when you're factoring, you're supposed to factor completely. X plus 1 is factored completely. There's no GCF there, and there's no higher exponents. So that means it's definitely factored as much as possible. X squared minus 4, however, this is factorable. It has a special name that we have gone over. It's a difference of squares. You can say that it's a squared minus b squared, which that formula is a plus b times a minus b, which we said you better have memorized. So I'll leave that original GCF in blue just for consistency. And then factoring x squared minus 4 gives us x squared plus, not x squared, pardon my mistake there. I was looking at the 2. X plus 2 times x minus 2. And if you don't trust it, FOIL that out. You will get x squared minus 4. All right. Well, now x plus 1 is factored. There's no exponents, no GCFs, no exponents, no GCFs, no exponents, no GCFs. So we can go ahead and set each of these things equal to 0 and solve from there. So x plus 1 equals 0, or x plus 2 equals 0, or x minus 2 equals 0. Very easy algebra to finish this. I hope subtract 1 on both sides of the first, subtract 2 on both sides of the second, add 2 to both sides of the third, giving us solutions of x equals negative 1, excuse me, looking at another number, negative 1, negative 2, positive 2. Those are our 3 solutions. 3 solutions. 1, 2, 3. Now there's a cool feature about polynomials in that the largest exponent you see is the maximum number of unique solutions. This is something that we'll kind of address later, but I'm just kind of spoiling for now. But the point is, if this was an x squared, if that was the biggest exponent, we couldn't have 3 solutions, we could only have 2. If this was an x to the 5th, we could have up to 5 solutions. But we also know that solutions can be repeated, as we've seen previously at least once. So that's why I said unique solutions. You could have x to the 5th minus 1 equals 0, and maybe you think there's only one solution. Maybe it is, maybe it's not. We're not going to get into that problem. It's got some other things going on along with it. We don't know how to factor x to the 5ths, right? So again, not going to do a whole bunch of these. We already did 2 of these examples last time with quadratics. It's just solved by factoring. If you see a problem that you think you can factor, it's probably the quickest way to solve it. If you don't think you can factor it, then you tend to go to one of these other methods like the quadratic formula or completing the square, if it was quadratic. But you couldn't do that here. This says we have an x to the 3rd, so we can't do the quadratic formula. We can't complete the square. Maybe there's other methods to solve this one. Maybe we don't know them. Maybe we're not taught them in this class, but there are other methods. In fact, there is a cubic formula, but it's not pretty at all. You don't want to have to memorize that. All right. So make sure that your factoring is up to par. We'll be factoring all semester. My point was not to teach factoring, even though I probably spent half a class going back and doing it anyways, because I like to be a little nice. All right. So the next topic, the next type of equation that we'll be covering are radical equations. Now remember, radicals are square roots, cube roots, fourth roots, fifth roots. It's things like this. It's like having the square root of x minus 2 is equal to x plus 9. This is completely made up on the fly. The solution is probably ugly. We're not going to solve it. I'm just saying that that's what I mean by radical equation. It's an equation with a square root or a cube root, some type of root in there. So a lot of people like to go and blatantly memorize these list of instructions, and that's fine, but if you want to have higher learning, it's more about understanding why we're doing these things. When we're solving equations, the main goal is generally to get x by itself by unraveling, by doing things in opposites. And one thing that we pointed out before is that square roots and squares are opposites. Whoa, that was a weird pen move. So before we had something like x squared equals 100, and we would take the square root of both sides. Question mark, question mark, question mark. Was that all we did? And then if this was regular class, someone goes, no. You had to have the plus or minus, at least I hope. And it's usually only one person that says it this early. And then I go, don't forget that you have got to remember this. It will follow you for the rest of your mathematical careers. And we did that because we get the x equals, and then the right side is just whatever it happens to be. Of course, the plus or minus is still there. So the solution to that would be plus or minus 10. So again, it's about the y. We had x squared isolated, and to get rid of it, we took a square root because square roots and squares are opposite to each other. So we're going to go with that idea for radical equations, but instead of seeing a square and we need to square root it, we'll see a square root and we need to square both sides. Or we'll see a cube root and we need to cube both sides. So that's why we isolate a radical. This word a is because there could be a second one of them. There could be 3 in a nightmare problem that you would never see in this course. But if there are multiples, then you just pick one to isolate because it's generally going to mean you have an extra step to take later. And we will see one of those, don't worry, he says with an evil smirk. So once you have the weird part isolated, like we isolated the square and then we square rooted it, so now we isolate the weird part because it was a square root, we would square both sides. We would raise both sides to a power that matches the index, which means square root, we square. So that's the opposite order of what we had before. Now I need to point something out that's critical. This plus or minus was necessary when you're going from x squared and you have to take a square root of both sides. This was that loss of sign generality we talked about. This is going to be a constant issue with you. You're going to be constantly battling this, especially because I'm about to give you something that doesn't have it, but that's because it's a different perspective. So when it's x squared equal to a number, you plus or minus square root both sides. I did not say plus or minus anywhere. There's no plus or minus needed. When you go from a square root and you square both sides, there's no loss of sign generality. And I'm going to erase all this little scratch work in just a, well, I guess I don't have to. I'll leave it. So what I'm saying is, let's say you had the square root of x is equal to 10. This is the problem we have now. This is a new problem. What these instructions say, isolate the radical, which it's already done, raise both sides to a power that matches the index. So that says you're supposed to square both sides. Because that was a square root, so we square both sides. There's no plus or minus here, and what you end up with is x equals 10. The square roots and the square cancel. 10 squared, I said 10, I meant 10 squared, which is 100. Now, if you think there's supposed to be a plus or minus here, so I'm going to put a little red plus or minus question mark. If you go back and try that in the original problem, if you plug it in here, if you plug the 10 in, it'll work. That's a check mark because, I'm sorry, 100. The square root of 100 is 10. But if you put the negative 1 in there, if you put negative 100 in here, the square root of negative 100 is 10i. Because you have a square root of a negative, which means you pull out an I, and 10i is not equal to 10. So that one would not work. So that's kind of the logic and reasoning as to why there's no plus or minus with this one. There is no loss of sign generality. You're not squaring it and unraveling it. It was never part of the problem to begin with. These subtle details will make or break you. If you forget the plus or minus when you need it, you're wrong. If you use it when you're not supposed to, you're wrong. Now, you can always go back and check your solutions. That'll help you with this one, because if you do throw the plus or minus in, you'll always eliminate the minus one unless you make a mistake at moving forward from there. So isolate the radical. Raise both sides by a power that matches the index. Now, with most simpler problems, you won't have step 3. Step 3 is a pain in the butt, though. If you go through step 2, if any radical remains, you have to basically start, I don't want to say start from scratch, because you're not going back to the original problem. You just go back to step 1, and you should only have one radical left over. You'd isolate it and raise both sides to the 2 or 3, whichever you need to do. Step 3 is just an if statement. It doesn't always happen. It doesn't usually happen, but I will give you one. From there, you solve via any method you need, factoring, quadratic formula if it's an option, whatever. Now, there is an extremely important step here. What does that say? Check your solutions if the index is even. So if you had a square root or a 4th root or a 6th root, you 100% have to check your solutions. So there's an opposite problem to that loss of sign generality. The loss of sign generality means we had to introduce the plus or minus. It could be 2 solutions. But when we square a square root, there could have been something inherently that makes the inside of the left side not match the right side before squaring it, the sign issue that we might not be able to see. So what can occasionally happen is you'll get a solution, you think it works, you check it, and then it fails. So this, I believe, is the first instance of equations where you have to check your solutions. Now, I did say if the index is even. Now, a lot of students will take this statement and say, well, that's only half the time, so I'm just never going to check them and hope for the best. Well, here's the thing. I would say like 95% of the time, I give you even indiced radicals to make sure you are checking your solutions. So this is going to be critical. So what I say in parentheses is if you can't remember the condition to check it, just always check it. Always check it. This is something you can always do no matter what. But there will be solutions to these equations that do not actually work. We will find one, it looks like it works, but then when we try it out, it fails. So don't forget to check your solutions. All right. Example 2. Solve the equation. Here we go. A, we're going to have the square root of 3x plus 5. Then outside of that will be a plus 9, and then it equals 2. So remember, equation solving is generally about isolating the weird part and then doing the opposite of that. So x plus 5, the weird part is the plus 5, so we subtract 5. X times 5, the weird part is the times 5, so we divide it. X squared equals something, the weird part is the square, so we square root it. We isolate a square root, we can square both sides, but you can't just do it now. I cannot square both sides yet, because you have to isolate the radical. That means to get it by itself. So what I'll have to do first is move the 9, so let's subtract 9 on both sides. Given us, is this going to be enough room? I'll make it work. The square root of 3x plus 5, all under the square root, then equal 2 minus 9 is negative 7. And it's at this point that we can square both sides. So this is the easiest way to do it on the left, the square root and the square. That's saying it applies to the whole thing, but you don't need this parentheses. That's up to you. Now, if I do it this way on the right, it's wrong though, because that's a negative number, so you got to make sure to wrap it in parentheses. So let's go over here. So square roots and squares cancel, so that's just a 3x plus 5 on the left. Negative 7 squared is positive 49, not negative 49. And then we just solve. We're already at step 4. Step 3 is skipped. If there's any radicals remaining, which there are none, so we skip step 3. To solve this, there's no x squared, no factoring, just subtract 5 on both sides, and then divide by 3. That does not divide evenly, so we get x is equal to 44 over 3. It doesn't reduce either. Now here's what some people will do on a test or a homework. All right, I got the answer, box it up, ship it out, we're done, yay. Happy face, whatever. Nope, you're not supposed to have done that yet. Now this is something that I reserve the right to go back and check. On your test, there's no spot in my math lab that requires you to check your work, but I can go back to the work that you are 100% required to submit to me I can go back to that and look, all right, well, let's see if Bobby on his, whatever, problem number 5, I know that was a radical, he got it right, but did he check his work? So I can go back and look, and all I see is this. I don't see the checked work. And then I can go, well, sorry, Bobby, you didn't do everything properly, so I'm actually going to lower your test score a couple of points. Because if this wasn't a computer-based test, you would have never got the points to begin with. You didn't deserve them. So please make sure that you are checking your work. And I'm just going to do that right here. So for the checking, what do? We just take the solution, we plug it, which was the 44/3, we plug it into the x and see if the left side matches the right side. So we get the square root of 3 times 44/3. You're like, oh no, a fraction plugging it in, this is awful. Don't worry, it's not that bad. Then the plus 9. This is what I like to do when I'm checking something. I put a little equals over the question mark, a question mark over the equals. Because we're questioning this. Oh, no, fractions. Well, guess what? They clear out really easily. Those 3's are gone. The top and bottom of a product. So that's just the square root of 44 plus 5, then a plus 9 outside. We're saying, is that equal to 2? 44 and 5 make 49. So that's the square root of 49 plus 9. Is that equal to 2? Square root of 49 is 7. 7 plus 9. Is that equal to 2? Well, 7 and 9 is equal to 16, which is definitely not 2. That's a false statement. So that means the solution does not work. So the one solution we found didn't work, which means there is no solution. Or the Greek letter phi, which means the empty set. You might see curly brackets with a little sentence kind of attached to it. There's all sorts of different ways you can write that. So just like in the real world, there are some problems that don't have solutions. There's no solution to this equation because when we squared this square root, the right side was a negative number. The left side, the square root of anything, has to be a positive number if it's real. So this was already a problem. So in red, I'm going to make this little note. A really analytic student would have gotten to this point, the square root of 3x plus 5 equal to negative 7. You can stop here. Already at this point, I know there's no solution because the left side, this is a positive number, a square root, no matter, because we're only dealing with real numbers. We don't solve equations and get imaginary numbers outside the quadratics for various reasons. But this is supposed to be a real number. We're only solving for real numbers. So square roots of any real number is always a positive. Square root of 4 is 2. Square root of 9 is 3. The square root of 17 is like 4.2 something or 4.1 something, blah, 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 blah. So the left side has to be a positive number, but the right side is negative 7, which has to be negative, which is false. That looks like fable. False. Positives are not equal to negatives, so we could have gone ahead and said no solution. It's a shortcut. Are these no solution situations always so obvious? Absolutely not. If there had been any variables on the side with the 7, we could not have made that analysis because variables can be positive or negative, so they could negate each other. This is just a very specific situation in which you could shortcut the problem and only really do one step. One step, boom, oh, nope, no solution. This red ink is exactly how I would do it because I know special scenarios in which we can shortcut. Right, so this is a pretty normal problem right here. This is what you'll usually see in the homework. If I was going to give you a test with like 6 or 7 of these, 5 of them would be this. But the other one, the other 1 or 2, just one really, would look like this. And go ahead and buckle up. The square root of 3x plus 1. Then another square root after a minus, square root of x plus 4. is equal to 1. So I said if I were going to give you a test with 7 of these, 6 would be like A and 1 would be like B. If I were going to give you a test with 2 of these, 1 would be like A and 1 would be like B. So I still would want to get the full spectrum of types of problems. Because when you go into calculus, that full spectrum is still there. It's not like, hey, let's just do the easy stuff and never think about the hard stuff. No. It's always going to sneak up on you eventually. So why is this problem more challenging? Because there's 2 radicals and that whole step 3 that if this happens, it's going to happen now. So let's pull the instructions back up just for a few moments. Isolate the radical and then raise both sides to a power that matches the index. So isolate a radical. A means there could be multiples, and there sure is. So once we pick one and isolate it, we'll square both sides because these are square roots. I'm not even going to do any examples with cube roots. You might have one in the homework, but I pretty much already hinted that the test is going to be square roots because it forces you to have to check them. And that last example, if this was a test question, if you stopped with the 44/3, you definitely would have gotten no credit because it was no solution, it failed. You don't want that to happen. And it's a flip of a coin. All right, so which one's easier to isolate? Me personally, I think it's easier to isolate the first one because we can just add that square root to both sides. So let's add this square root of x plus 4 to both sides. That square root counts as one entity, so you have to do it all at once like that. All right, so that gives us the square root of 3x plus 1, then equals, the order of the 1 and the square root on the right don't matter. I'll put the 1 first just for simplicity's sake. So it's in the same order you see there. But a lot of people would put the square root first. Me personally, I would have done the square root, then the 1. And then once we have that square root isolated, so we have the 1 on the left isolated, not the one on the right, but that doesn't matter as long as we have one of them isolated. This is where we square both sides. I'm going to write this incorrectly at first. The left side is fine. Squaring a square root looks like that. That's fine. This is wrong, though. And you might say, well, what's wrong about it? You're squaring the square root. That's the same thing you did on the left. On the left side, there was no 1 and a plus in front of it. This squaring has to be the entire side. So to fix that, and this is going to be a very common issue, you got to wrap it in parentheses. Now, that right-hand side, how much room am I going to have here? Yeah, I'm going to need to just do some side work over here. And in fact, I didn't want to do that in red. I wanted it in blue. That's okay. Quick fix. So let me just have some side work. Because this right-hand side, and we'll do that in red, this right here, the right-hand side, the 1 plus the square root squared, oops. What you have to do with this is, well, hold on, here's what people will do wrong. They'll say, oh, just square the 1 and square the square root. So what I'm about to write is wrong. They'll say this is 1, and then the squared and the square cancel, so 1 plus x plus 4, and then they'll maybe add the 1 and the 4. This is wrong. That's only half the work. You cannot just square the first and the last term. That's not the way it works. You might be thinking, well, that's how it is with difference of squares, and you just make a minus between them. Difference of squares is all about the outer and inner canceling. What you need to do here is write the parentheses times itself, and then FOIL it. That's going to be a common theme. So foiling, the first is 1 times 1, which is 1. The outer is the 1 times that square root of x plus 4. So plus, I'll write the 1 just to be specific. So if this 1 was a 2, this would be a 2, square root of x plus 4. Again, that was first is this very first one. This 1 in the square root is the outer. The inner will be the exact same thing, 1 times the square root. So plus 1 square root of x plus 4. And then the last is the square root times the square root. Well, square root times the square root is the square root squared. Just like 5 times 5 is 5 squared. This is simplifiable, though. This, you cannot add this 1 and 1 and this 1. That 1 plus 1 is not a 2. You cannot add them because they're not like terms. Because this has a square root, this has a square root. This and this are like terms. It's like having y plus y. Y plus y would be 2y. This is like having square root plus square root, which would give us 2 square root. So again, this one right here is the very first one. Now I'm focusing on these. The 1y plus 1y, that's basically what's happening here, would be 2y. So it's plus 2 square root of x plus 4. That's another reason why I liked writing those ones in front of the square root. If I didn't write them, you might get confused, but you need to understand that moving forward because I can't always do everything for you, can I? And then the last part, the square root and the square cancel each other out. This square root and the square cancel each other out. So it's just left with the inside, which is a plus x plus 4. The very last thing you can do is there's a 1 and a 4 that can add to make a 5. No, you cannot add the 2 paired with the square root. That's like saying 1 plus 2x is 3x. No, 1x plus 2x would be 3x. The order that you write these does not really matter. I'm going to write the 2 in the square root first, then the plus x and the plus 5. Again, this 4 plus 1 gave us the 5 at the end. Now I'm going to take a little orange marker and say that here, now we're going back over here, so the left side, the square root and the square cancel, so we just get a 3x, get a little more room, 3x plus 1. The square root and the square cancel each other out. That was by design. That's what we wanted to happen. And then this parentheses squared, we just take our ending bit. That's what's going to go here. So equals 2 square root of x plus 4, then plus x plus 5 outside the square root. Okay. Well, unfortunately, after doing this, we can see there is still a square root. That didn't happen last time. After we squared both sides in A, all the radicals were gone. So that step 3 was unnecessary. This time, it's necessary because there is still a radical. We started with 2, and now there's only 1, so that's a good sign at least. So now we're just going back to the original starting instructions. Isolate the remaining radical, and then square both sides. Hopefully at this point, there will be no more radicals. Let me give myself some more space. There we go. All right, so what do we need to do? We need to move the x and the 5 first of all. We'll also need to move this 2. So let's subtract x on both sides. Let's subtract 5 on both sides. And that'll give us 3x minus x is 2x. 1 minus 5 is a negative 4. And then equals 2 in the square root. That's all that's left on that side. Now we're supposed to have the square root isolated. The 2 in front of it says it's not isolated yet, so we got to get rid of it. That's 2 times the square root, so guess what we do? We divide both sides by 2. You can do the division all at once or like this. It's up to you. I'm choosing to do it this way to reemphasize that if all pieces of a fraction have a common factor, you can reduce them. So this 2 and this 2 and this 4 will all reduce to a 1, and a 2 respectively. So that's x minus 2 now. Again, the 2x divided by 2 that made an x, the minus 4 divided by 2 made a negative 2. Again, the 2 goes into 2 once, and the 4 twice. That's where those came from. With the denominator of 1, you don't need to write it anymore. That only works if there's a factor everywhere. These 2's on the right side will cancel. It was in a factored form, which is why they canceled that way. There's no pluses or minuses outside of the radical. So that's just the square root of x plus 4. And now we're ready to, step 2 was to raise both sides to a power that matches the index. So we're going to square both sides. Now, I can square the right side like that. If I do it on the left, that's wrong because we'll need parentheses. And you have another binomial square. So some more side work. going from right here, the x minus 2 squared is really x minus 2 times x minus 2. I did show you a formula for that, the a squared plus 2ab plus b squared, or a squared minus 2ab plus b squared. If you're using those formulas, that's fine as well. And then you just FOIL that out, which will give us x squared minus 2x plus 4. I'm doing that one quicker because there's no goofy square roots. Combine the outer and the inner terms, which is x squared minus 4x plus 4. And then that, let's do a little yellow marker, is what this left side will become. So the left side is going to be x squared minus 4x plus 4. The right side is just going to be x plus 4. All right, no more square roots, which means this is officially an easier problem finally, right? Finally. But it's not linear. There's an x squared, which means the first thing we should probably try and do is solve it by factoring. If it's not factorable, then we quadratic formula it or complete the square. If you just want a quadratic formula or complete the square to begin with, that's fine, but you will have a more time-consuming problem on your hand. To keep the x squared positive, let's move everything left. So we need to subtract x and subtract 4 on both sides. Subtract x, subtract 4, and we'll get x squared minus 5x. The 4's actually cancel each other out, and then equals 0, which makes this a relatively easy problem to factor. It's just two terms, but it's not a formula. There's a GCF here. There's an x that goes into both of those. So let's pop an x out, parentheses. Dividing x squared by x is x, minus 5x divided by x is 5, equals our 0. Let's move this over here. The x times the x minus 5 equals 0. Zero product rule, set x equal to 0, set x minus 5 equal to 0. The first one's solved. For the second one, you just got to add 5 to both sides to give us x equals 5. I will not show that plus 5, minus 4 kind of stuff a lot moving forward, just FYI. So if a student does this right now, I will even spoil this, they will be wrong because the solution is not 0 and 5. Remember that you have to, whenever your index is even, check your solutions. If you don't know that condition, then just if you see radicals, check your solutions no matter what, even if it's an odd index. And I already said that I will be giving more evens than odds. Go away. I thought I clicked that first. So you got to check it. All right, so we got to go back to our original equation before we touched it at all, before we did anything. Now, here's one minor problem some students have. If you goofed up any of the work in the middle of this, the side work, the main work, the multiple squaring of both sides, there's a lot of room for error, right? You find these solutions, maybe you end up with 1 and -7. Well, they're both going to fail because you made a mistake earlier. And that is going to be a little frustrating, but at least, well, I don't want to say at least. And the problem is you might go, okay, well, it was just they were extraneous, like Mr. Beckner talked about. They seem to work, but they really don't. Well, unfortunately, it does turn out that you made a mistake somewhere else, so that error just kind of follows through. So you really do have to take your time and be careful with this. Lots of room for errors. All right, so back to the original equation, the square root of 3x plus 1, then a minus square root x plus 4 equals 1. So we'll do the checking here. Let's do it in blue. So for 0, we get the square root of 3 times 0 plus 5. Then, wait, nope, not plus 5. That's plus 1. I was looking at A for a second there. Then minus square root of 0 plus 4. Is that equal to 1? So the zeros are what I plugged in. That's 3 times 0. 3 times 0 is 0. 0 plus 1 is 1. So that's the square root of 1 minus 0 plus 4 is 4. So square root of 4. Is that equal to 1? Square root of 1 is 1. Square root of 4 is 2. 1 minus 2 is not 1 though, it's -1, which means x equals 0 has to be tossed out. It fails. Now you might say, well, that means 5 works. No, these solutions are completely independent of each other. There's no guarantee that one always works. I used to, when I taught this class called college algebra, my favorite thing to do was only give equations that had no solutions of this style, because it really reinforced the checking. And you might say, well, that made it easy. You already told the students what the answers were. But of course, I checked their work, and no work meant no credit because it wasn't an electronic test. All right, so that was the first one. The second one, we're going square root of, now we're plugging in 5, so 3 times not 0. 5 plus 1, then minus the square root of 5 plus 4. Is that equal to 1? 3 times 5 is 15. I'm going to do a couple steps at once. 15 plus 1 is 16, so that's the square root of 16. Minus 5 plus 4 is 9. Square root of 9 is that 1. Square root of 16 is 4. Minus square root of 9 is 3. And that is 1. So that means x equals 5 is the actual solution. We did have a solution this time. It seemed like they were 2, but it was only 1. I mean, that's just the real world right there. Sometimes we have problems with no solution. Sometimes we have problems where we think there's 10 solutions and only 1 actually works. It's another case of, I have what I think is a funny joke to go along with this, but I'm so skeptical to do some of my silly, not necessarily out of taste, but maybe they will be in 10 years. I don't want to put those on the internet. Again, they are very, very mild, but I'm not going to make the joke. Oh well. So as I said, if I were going to give you 2 of these style problems on a test, one of them would be like A, which is short and sweet, more to the point, and one of them would be more like B, where you really, really have to show that your algebra skills are on point. This is pre-calculus. Your algebra skills have got to be on point. Calculus itself, the idea of calculus is pretty much just a series of formulas you memorize and use. What people mess up in calculus is the intensive algebra where you're doing things of this level, you know, every other problem. So you've got to get used to this. You've got to become accustomed to this. All right, how are we on time? About 25 minutes. Rational exponent equations. You know I'm always honest about what's going to come up again and what won't. This isn't really going to come up again in this course. It is a fascinating idea. We actually just did one, believe it or not. We just did 2, in fact. But rational exponential equations. So a little reminder what a rational exponent is. The word rational means fraction, so it's an exponent that's a fraction. So it's something like x to the a over b. Well, it turns out that I reminded you, this was prereq material, that this is the same thing as the beef, that sounds like beef, the beef, B-E-E-T-H, root of x to the a. It's that the numerator of the fraction becomes the power inside the radical, and the denominator of the fraction becomes the index. So this is a formula that you have got to have memorized. You'll see occasionally throughout the course. I'm not saying you won't see this again in the course. You will still see this frequently in the course. Not frequently, but enough. Several times. We just really won't be doing a lot of rational exponential equations. So the point of this is rational exponents are the same thing as radicals. So the list of instructions for this is pretty much, whether it appears to be or not, the same thing as the list of instructions for this, but we don't give you the if one remains because it's just nightmare fuel if you did the steps here and one still remained. So these are always a little simpler in format, even though they look scarier. So what do we usually do? Isolate the weird thing. Isolate the term that has the rational exponent in it. Then what you're going to do is to get rid of it. So we have this exponent. We have an a over b, this exponent up here, and we want to get rid of it. How do we get rid of an exponent? Well, if you had a square, you'd square root both sides. If you had a square root, you'd square both sides. And this thing has that feature in it, so you actually do both of those things, not necessarily squares specifically. The numbers are dependent on A and B. So you would actually raise both sides to the B power and then take the 8th root of it. But you don't want to do it in that format because you're mixing formats. It's like talking about dollars and yen in the same problem. Just, why not have everything in terms of one form, right? So the equivalent step is what it says in step 2. Raise both sides to a power that is the reciprocal, which means flip it, of the original exponent. So you'll have something like this. X to the A over B equals a number. What you are doing is you are raising both sides to the reciprocal of this fraction, to the B over A. You do it to both sides. Why do you do that? Because now you have a fraction times a fraction where the tops match, so they cancel. Top and bottom match. Bottom and top match, so they cancel. So that's now just a big giant 1, x to the first. It's done. That's the idea of step 2. 3 asterisks must be a super important note. If the numerator of that exponent was even, you need a plus or minus. What this is relating to is having an x squared equal to a number. So if you have x squared equal to a number, you had to take the plus or minus square root, not just a square root, a plus or minus. If the numerator is even, that's like having this even numerator, because x squared is the same thing as having x to the 2 over 1. It had an even numerator, so that plus or minus was needed. These steps kind of relate to each other. Not kind of, they absolutely relate to each other. Because x to the 2 is the same as x to the 2 over 1. So with that 2 being in this format, we know we needed a plus or minus. So in this format, we'd know we'd need it as well. If that had been an x cubed, there would not have been a plus or minus. We would have just cube rooted both sides. If that had been an x to the 4th, we would have needed a plus or minus needed. X to the 5th, we wouldn't need it. So this is another extremely subtle detail that people can miss and mess up. Sorry for all the clicking. But I took up a little more space than I wanted there, so I'm just starting over. Not starting over, but just going back to only the instructions. But once you have the weirdness gone, no more exponent, solve via your traditional methods, and then check your solutions. A lot of people like to skip the checking here, but you are supposed to check. It's another case just like the last one where you only have to check if it was an even denominator, but with all these conditions on the numerator and the denominator, it's probably just in your best interest to check your solutions no matter what. What you might want to do is say, all right, well, I don't know when the plus or minus is necessary, so I'll always do it, and then just make sure you're always checking, and in the cases where you weren't supposed to have it, the minus will go away. It'll be fluid, in fact. Excuse me, if you heard that. That's not what I wanted. All right, example, what are we up to? 3. Oh. And of course, check is necessary. I don't like putting that part of the instructions in there. I swear this is misbehaving lately. What? There we go. And in fact, not an A, we're only gonna do one of these because I said this is a problem I don't do a ton of, we don't see a ton of. I'm not saying we don't see rational exponents frequently. I'm saying we don't really solve equations that look like this frequently. So 5 times x to the 3/4 minus 10 equals 0. So per usual, the main first thing you're focusing on is isolating the weird part. That's what each of these steps 1 have been essentially. So we're going to need to move the 10 first by adding 10 to both sides, which will give us 5 times that x to the 3/4 then equals 0. And then we need to divide by the 5, which will give us x to the 3/4. What happened? I wrote 10 and it only came up as 0. 10 divided by 5 is 2. There we go. So x to the 3/4 is equal to 2. The weird bit is isolated, so now we unravel the weird bit. How do we solve equations? Isolate the weird bit, unravel it. with quadratics and polynomials, that's usually not the case. It's, factor, formula, things like that. But we're talking about the weird equations, like radical exponents. What? All right, so now what we're going to do is take this x to the 3/4 equals 2. We raise both sides to the reciprocal of that exponent. So I'm going to raise both sides to the 4/3. I don't need a parentheses on the right because it's just a 2. Now I'm going to ask us, and then erase it after, do we need a plus or minus? Yes or no? Well, let's look at that condition that you have to memorize for testing situations. If the original numerator was even, you need a plus or minus. So if the original numerator was even, that means you had something like an x squared, which was plus or minus square root to get rid of it. This was a 3 though, that's odd, so there is no plus or minus needed for this problem. Let me just go, yeah, let's just leave it there. It's fine. So what happens? The 3's cancel, the 4's cancel on the left side. The only thing that's left over is a 1 now, and you don't really need to write x to the first. You can, but most people just write x equals 2 to the 4/3. Well, I don't know what 2 to the 4/3 is off the top of my head. It's in that funky notation. And in fact, quite frequently, it's fine to leave it in that notation, unless this is simplifiable off the cuff, unless you know what the cube root of this is, and then you can take it to the 4th power. But if you do 2 to the 4th, that's going to be 16, and we don't know what the cube root of 16 is. Remember, did I erase it? No, I did not. That something raised to a fraction is the same thing as make the denominator the index and the numerator the power. So that 2 to the 4/3 is the same thing as the bottom's a 3, so cube root, top was a 4, so 2 to the 4th. 2 to the 4th is 16, so that's the cube root of 16. We know the cube root of 8, but not the cube root of 16. Now this could be simplified. You could write this as the cube root of 8 times 2, and then the cube root of 8 is 2, so that's 2 times the cube root of 2. Now admittedly, that is the best form out of the answer in the grand scheme of things, but because the original problem had rational exponents, I think it's okay for the exponent to have rational exponents. And it's less work, so that's kind of nice. But just know that if you did want to know, well, what exactly is this number? How can I think about that? Because nobody can ever think about rational exponents in a traditional sense, even your teacher. Because this is 2 times itself 4/3 of a time. That'll just make your head explode. Well, it turns out you can simplify it a little bit, but it's not a whole number. It is still an irrational number. All right. 15 minutes. Next up. Oh, interesting. I just realized I did these in a backwards order, the last two, but that's not a problem. It doesn't matter. We have to cover them all. They're independent of each other. Absolute value equations. This right here is extremely important in the grand scheme of things. Calculus, calculus 2, differential equations, especially when we segue into something called absolute value inequalities, which we'll study in the next couple sections. You get into this concept known as a radius of convergence in later calculus courses, where you're trying to approximate a function with an infinite series of functions. And I know that probably sounds terrifying, but what you can do is you can actually, instead of calling it an infinite series, you can just say use the first 10 or 11 terms, and then there's a small region in which it actually works. And I know I'm speaking over your heads. I'm just trying to give you a reason as to why this is important. Absolute value equations. Hey, absolute values are a little weird, so maybe we should isolate the weird part first. Surprise, surprise. All right, now here's where things get interesting. There's an if condition. If the number by itself, once the absolute value is isolated, once you have done step 1, you have to do step 1 first. If the absolute value isn't isolated, this analysis in step 2 might be wrong. So absolute value is by itself. So it says something like absolute value of x equals 12. If the number by itself is not negative, you're going to make two equations out of this. You're going to set the inside equal to the positive of the original number and the inside equal to the negative of the original number. Square roots and absolute values, I'm sorry, let me start that over. Squares, quadratics specifically, and absolute values have a ton of overlapping ideas. So when you have x squared equal to a number, you take the plus or minus square root. When you have the absolute value equals a number, basically you're just setting it equal to the plus or minus of that number. Because just like when you square a number, if it was originally negative, it becomes positive. When you take the absolute value of a number, if it was originally negative, it becomes positive. So there's a lot of similarities. So this step 2 is like our plus or minus. Here's where people make mistakes though. They'll change the sign of the inside of the absolute value. Nowhere does it say that. So if the original inside is x minus 3, it's x minus 3 both times. It would be something like x minus 3 equals 5 and x minus 3 equals negative 5. It's the thing by itself that is changing signs. And again, this is to counteract that loss of sign generality. When you take an absolute value, you don't know what the original inside was, so you say both cases were possible. That's what we're doing in step 2. Solve them, check as needed. There's conditions as to when you need to check, when you don't need to check. I'll kind of explain that as we go through it. And example 4, solve, big surprise. And we're going to do 2 of these. So A, this will be the absolute value of 2x plus 3. Then a minus 7 after the absolute value equals negative 2. Oh, if the number by itself isn't negative, it's negative. So just ignore that stuff. Nope. Has to be isolated first. Did that on purpose. So we got to get the absolute value by itself. So we add 7 to both sides, which will give us the absolute value of 2x plus 3 is equal to 5. Negative 2 plus 7 is 5. So I don't know if the original x is a positive or negative number or whatever. There's 2 possibilities in general, because we can have something that makes the inside 5 and then it'll be true, or the inside could be negative 5 and it'll also be true because the absolute value of negative 5 is 5. I'm not saying x is 5 and negative 5. I'm saying whatever makes the inside those values. So here's our 2 equations. I'm going to go red for showing the 2 equations. The first one is 2x plus 3 equals 5. The first one is just dropping the absolute value essentially. The second one, leave the inside alone. Don't make that a minus. It's the 5. It's the number by itself that changes signs. And then just do your algebra. The algebra is going to be pretty coincidental. You're going to subtract 3 on both sides for the first equation. You actually subtract 3 on both sides of the second equation, which will give us, for the first one, 2x equals, you don't have to do these simultaneously. So 2x equals 2 and 2x equals negative 8. Watch your signed arithmetic. 2x equals 2, divide both sides by 2, and you're done. X will equal 1. 2x equals negative 8, divide both sides by 2, and you'll get x equals negative 4. I know these are correct because when the absolute value is isolated, this was a positive number. That's the condition at which you have to check if the absolute value is equal to a negative, which is kind of weird because instead, if it's equal to a negative, I'm just going to shortcut things ultimately, as we've seen before. So if you don't trust this, plug the 1 in, it'll work. Plug the negative 4 in, it'll work, but I'm going to leave that to your own time to do. B, 4, absolute value, 7x minus 12, then a plus 40 equals to 10. Oh, that's a positive number, so we know we're going to do these 2 steps. Well, again, jumping the gun, isolate the weird part first. Got a 4 times and a 40 being added. It's easiest to move the 40 first by subtracting, which will give us 4 absolute value, blah, 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 equals negative 30. The 4 is times the absolute value, so to undo that, we divide by 4. Now the 4 won't go into 30 evenly, but it will reduce. Let's make that not look like a 17. To a negative 15 halves. Now, what some people will do is they'll do this. And well, I pulled out red earlier for the splitting. I won't actually write it. This is what some people will do. They'd say 7x minus 12 equals negative 15 halves, and 7x minus 12 equals positive 15 halves. And they would go through the arduous process of solving those because there's fractions. You could multiply everything by 2 to clear them, or you could be stubborn and just put up with them the whole time and not listen to your teacher's advice. And you'd get two numbers. Oh, I don't know what they are off the top of my head, but then you'd have to check them because you're not really aware of the condition to check it. The condition to check it, as I lightly said, and I lightly said it because I'm going to give you a better statement, was if this is negative, once it's isolated, you have to check it. There's something better though. I know right now, because I have an absolute value, something that is always positive, right? When you take an absolute value of something, it's positive, equal to something that's negative. We made this analysis earlier when we had a square root equal to a negative. Square roots are always positive, but when it was equal to a negative, that made it a no solution. That was the one of the cases where we threw out a solution when we checked it. Positive, negative, those two things are not equal to each other. That's false. So that means there's no solution. If you actually went through and found those two numbers, and check them, they would fail miserably. I can guarantee that. Guarantee. Real quick, C that I always do, even though I don't have it in my notes, but I always do it anyways. 3x plus 5 equals 5. 3 absolute value of 3x. I forgot the absolute value. There we go. I did it in blue at first for emphasis to make sure you caught me adding it in. So absolute value of 3x plus 5. First things first, move the 5, isolate the weird part. So it gives us the absolute value of 3x is equal to 0. Well, that's not a negative number, so we can do the two cases. We can set the 3x equal to 0, and we can set 3x equal to the negative of the number negative 0. But negative 0 is equal to 0. That's a terrible looking asterisk. There we go. Negative 0 is equal to 0. So this is really the same two equations. We've seen this type of scenario pop up in passing. You don't need to show the work twice. You can just show it once, divide both sides by 3, and you get x equals 0. Same thing here, x equals 0, divide both sides by 3. It's only one solution. So these absolute value equations can have one solution. This is a repeated root. We've seen that before with quadratics. They can have no solutions. They can have two solutions. They have one solution sometimes only when the absolute value once isolated is set equal to 0, because plus or minus 0 is always 0. It's an overlapping scenario. We talked about that with the quadratic formula. When we had plus or minus the square root of 0, the plus or minus just basically goes away, giving us the one solution. All right, so to finish today off, we're just going to eyeball the last set of instructions. We will go straight into this on Wednesday. The last type, equations in quadratic form. And this is, do I want to say my favorite type? If it's not my favorite, it's my second type. It's my second favorite type. It's one of those two, for sure. Quadratic form means that you can turn the original problem into something like x squared plus 2x plus 3. Whereas it might have started out as x to the 4th plus 2x squared plus 3. Or maybe it was parentheses 2x plus 3 and then closed squared plus 5 parentheses 2x plus 3 closed parentheses plus 4. So there's these things that while their graphical behavior are not necessarily quadratic, that they are in a form that with a substitution, with what we call a change of variable, going from a standard American dollar to a yen, will actually turn it into a problem that is quadratic, and then we can fall back onto the either factor it, quadratic formula it, or complete the square. But I will tell you that any problem I give to you in pre-calc I guarantee that the problem is solvable by factoring. If something is in quadratic form and you're supposed to solve it via this method, I can guarantee that once it's in quadratic form, it is factorable. That's a guarantee. Is that true in the real world? No. You might have to do the quadratic formula or completing the square on that, but that's a lot nastier. It's a little above our pay grade for now. So I am guaranteeing that if you see a problem that you think is in quadratic form, if you get it to be this, something like x squared plus 5x plus 4, there you go. It'll be factorable. But we're going to use a substitution. We don't want to use the same variable. If we start with x, you need to switch to a new letter. Now the word substitution, the first letter is s, which is a really terrible looking variable because it looks like a 5. So we use the letter u instead. So we say let u equal whatever the middle term's variable factor is. When we do that, naturally, if you square u, you will end up getting the leading term's variable factor. And once you change everything to u, so you convert your American dollar to your yen, you will end up with an equation that'll have just a u squared and a u, and it will be solvable by factoring in this course. Once you solve that by factoring, a lot of people will think they're done. Well, I just gave you a problem in the American currency, and then when you solve it in u, which I said was yen, that means you're giving me an answer in yen. If I ask you how many dollars does a steak cost, and you answer 50,000 yen, I'm going to go, I don't care. I want to know how much the steak is in the standard American dollar because that's the reference I gave you when I asked the question. So if I give you a problem in x and you turn it into a u, when you get down to the point where it says u equals 3 and u equals 4, that's not solved. That's your yen. You have to go back to your American dollar. So it means you'll take the u solutions, plug them into your let statement, and solve them for x. And the degree of difficulty here will vary. Sometimes you'll be squaring things, sometimes you'll be plus or minus square rooting things, maybe something a little else unique. Some of these you'll have to check. When will you have to check them? If your original equation had square roots, you'll have to check them. If for some reason you had rational exponents with even numerators, you'd have to check them. If there were absolute values somewhere, you'd have to check them. You could just blanketedly always check them. That's a good idea. But the main one is that if there were any square roots, you have to check them. That is the primary case where you'd have to check this type of problem, just so you know. So yeah, we'll call it a day there because we only have like 60 seconds. So we'll rediscuss these instructions next time, and we'll do several examples, at least 3 of them, next class. So that'll be finishing 1.6 for us then, but we have not finished it yet, which is why that homework due date is not a week from today. It'll be a week from Wednesday's class. What's that, the 23rd? So it'll be due the 30th. All right. So if you have any questions, please shoot me an email. I did want to mention that if I haven't mentioned before, I have a lot of things going on right now that can cause some noise in my home. And if that happens to have to be during our class, what I'll do is pre-record a class. And I'm not saying this is definitely going to happen. I'm saying that's maybe going to happen. This has already happened for my my Tuesday, Thursday classes. They got hit last week. So it might happen for my Monday, Wednesday classes in the coming weeks. And anytime that happens, I will record ahead of time. I'll make sure it's ready by the time class would be. I just wouldn't be broadcasting it live. It would just be directly on YouTube. The link would still be in Canvas. So again, just letting you know ahead of time in case that ever has to happen, which it probably will sooner than later. All right. So thank you. Have a good one. We'll see you Wednesday. Take care, everybody.